Hi, welcome back. This is another video on energy bar charts. In this one I'm going to quickly go through a number of examples you could use in your class. So how I teach this right from year 11, 12 and 13 is I have whiteboards. I have mini whiteboards that I've made myself, which are quite sizable. And the way I use them is I get the students to write their energy bar charts on these whiteboards, and then we share them. And it's the discussions that the kids have with each other about, oh, why did you have this much gravitational energy, and why did you have zero gravitational energy at the end, or whatever. All those discussions that the kids have, those are the learning opportunities. Just simply doing them on a piece of paper and marking them yes or incorrect, I just find doesn't get as much thinking going on. So if you don't have mini whiteboards, or there's no chance of you to make them, I'll use A3 sheets of paper where the kids work in a group, put their energy bar chart on A3 bits of paper, and then we come and stick them to the board and we talk about them. Or even they could do them themselves, and you could ask different groups. Group 1, could you come put your answer for question 1 up on the board, do a big energy bar chart, and then we'll discuss it as a class. It's those discussions where the kids get involved that are really, really useful and meaningful in terms of learning opportunities. So here's just a couple of examples. I'm going to go through these really quickly that you could ask. So in this situation, we've got a toy roller coaster, and it starts off against the spring here. This is position A, or the initial position, and then the spring shoots it and it goes up here to the highest point. It's still moving, obviously, and you'd ask the kids to do an energy bar chart for that. So they'd go through that process. They'd say, okay, what's my system? Which in this case will probably be the I've got the cart, the earth, the spring and the track, so just everything is involved. And in this case you can see there's elastic potential energy. I've given it 5 bars, but again this is where the kids say, oh, why did you decide to give it 5 and not 3 or 4 or whatever? And then I've called on my zero gravitational energy point, this platform here, so it has 0 to start with. It's up high at point B, so it's got some gravitational energy, and it's moving, so it's got some kinetic energy. But I know through conservative energy that my total energy before, my total energy afterwards have to be equal. So you can ask variations on that, and this is where it gets really interesting. So the kids have done this one, then we say, okay, do the same one, but now the track has friction. Okay, so some of that energy is not going to make it to kinetic energy at the top. Go ahead and draw that. And then they go and they'll draw that. They'll all have slightly different answers, and when you have those discussions with them, then you can pick up, why have you got that and why have you got that, and they start working through these ideas. So you can do the toy roller coaster, another variation where you go back to the first example. It's exactly the same, but the spring's not part of the system. So if you remember from the last video, that means that work has to be added to the system because the spring's in the environment. Or you could do, hey, it's the same as the first example, but it's still on its way up. It's not at its highest point yet. So another thing to get them really thinking. Another example is you can have a bungee jumper. So they start up high and then they get to their lowest point. You can choose the water to be the 0 energy point. So at this point they still have gravitational potential energy, a small amount, because they're not at the water. But they have no kinetic energy, and you'll go through and work through that. A variation on that one is you could say, hey, choose the bungee cord to be outside the system. So you'll have work going out of the system. You can do the well, where you have a bucket at the bottom of the well and you lift the bucket to the top of the well. The point of this one is that although the bucket is moving during the lifting phase, by the time it gets to the top, it's no longer moving. And so they have to be able to realize that they're only caring about the initial state and the final state and not what happens in between. So variation is you can choose the person to be outside the system. You could do 2 sets of energy bar charts here, one for a ball falling and one for a ball rolling down, but they're from the same height, so the change in height is exactly the same. And so you'll end up doing 2 sets of energy bar charts for this one and compare them side by side. As a level 3 extension, you would ask them to have bars for translational kinetic energy and rotational kinetic energy to see how its speed changes in these 2 situations. The 5th one, you can have just a car going at a steady speed, but it's going fast enough that some energy is transferred to thermal energy. So that's an interesting one there, where you talk about, well, actually, when you draw the energy bar chart from this, you actually see that the chemical potential energy of the petrol is being transferred directly into thermal energy. It doesn't get put into kinetic energy at all. The kinetic energy stays the same. Some for heating and cooling. They don't all have to be mechanics. So they've got a hot cup of Milo sitting on a bench. And so in this case, unlike everything we've done in mechanics, there's always a change in position. Here there's no change in position. We're just thinking about a change in time. So the initial and final states are the same coffee cup, but just, a couple of minutes apart. And so you're going to have energy being transferred out of the system in the form of heat. And you can go into depth with that if you want to say, well, in this case, the transfer is convection or conduction or radiation or a mixture of the three. You can have variation on this as you start with the same hot cup of Milo, but this time you put it in the fridge to show that it's the same cooling process. It just happens more quickly. And you can do another one where it's the same hot cup of Milo, but you put it in the microwave for a minute or so and see how it gets hotter and show how energy is transferred to that cup of Milo. So it doesn't all have to be mechanics. You can have some thermodynamics as well. Projectile motion, you can fire a ball up and do an energy bar chart for that. And then you'll compare that to, okay, now that the same ball with the same spring, same elastic potential energy is now fired at an angle. And so what's changed in those? So you'll do a separate set of energy bar charts to compare them. An interesting one I like to do is this pulley one, where you have a heavy and a light object that start at the same height, and you let them go, and obviously the heavy goes down and pulls the light one up. They're connected, so they're traveling at the same speed, but that doesn't mean they have the same kinetic energy. So the kids have to really think about this one, and it generates some really good discussions when they do their energy bar charts and share them. Another variation is you can get them to work backwards. So you can say, I'm giving you the energy bar chart. There's a million variations, infinite variations in fact. I want you to come up with a situation. And so they have to come work backwards and come up with a situation and share it as a class. And then the other students try and pick holes in it and say, that doesn't match this energy bar chart because of this and this and this. And finally, the second to final is I can use them in level 3 to show the photoelectric effect. So the photoelectric effect occurs when you have a photon that's absorbed by an electron in a metal. And if it has enough energy from the photon, it can escape and have some kinetic energy. So this is a violet photon. It has a lot of energy, so the energy of the photon is quite high. And because we're dealing with electrons, basically in chemistry, this is how they describe them, is that the electron's sort of bound in that metal and it has a negative energy. It's like it's in an energy well it has to escape out of. So if it has enough energy from the photon, 5 bars, to overcome that energy well, 3 bars, then the electron can escape from the metal when it's got 2 bars of energy, because we've got 5 positive and 3 negative make 2. Then if you change the color, so now we're at the threshold frequency, and this is a really good way of describing it for the kids to see what's going on, is that you've now changed the energy in the photon that's decreased. And in fact, in this case, we're at the threshold frequency, which is exactly the right amount for it to escape, but it escapes with no kinetic energy. So it's got no kinetic energy out of there as well. So energy bar chart's such a brilliant way of explaining the concepts that are going on in the photoelectric effect when you study level 3. The last thing I'll show you is there's a website. This is called Universe and More, where you watch a video, you choose the initial and the final state, and then you have to do an energy bar chart and check it, and it tells you if you're right or not. And there's a bunch of different examples there. Let me just find it. So you go to Universe and More, menu, games and apps, and I want to do energy bar charts. I've already done 1 out of 14 already. So you choose the event. There's lots of different things to choose from, and they have a video. So I'm choosing Felix, and so here's Felix, and he's falling, and the video just goes on repeat. So you can pause it at the initial state, which is there, and so you say, okay, at that point he's really high but he's not moving. So I go over here, what energy bar charts, if he's high but he's not moving, I'm going to have him gravitational, and let's give him lots of gravitational, as high as I can give him. Play it, and then in his final state, which is here, he's lower, so I'm going to give him some gravitational, but he's also moving, so I'm going to give him some kinetic. And I'm going to make sure that they add up. 600 and 400 is not 800, so there we go, 400 and 400. And check it, and I'm correct. Now it's giving me 1 tick, because what it wants me to do is it wants me to say, hey, you can actually go through this and change the system. So it's just Felix and not the Earth, and go through the same process and see if you can get it working. When it's just Felix, not Earth, then you've got to be doing work correctly as well. But it's a really useful tool, just the same as when I do this in the classroom. You could do these ones, the kids work them out on whiteboards or on pieces of paper and share the answers. The discussions that you get are really, really rich and useful. So I hope that's helpful. Any questions, you can get in touch with me for some more ideas. And if you have any ideas yourself, please put them in the comments. But it's a really useful way to get across the energy concept and energy conservation concept in a visual way that the kids can see what's going on really, really easily. Thank you.